Hello, my name is Zacharias. I am one of the authors of this paper titled Dynamic Embeddings for Interaction Prediction. In this study, we are interested in temporal interaction networks, which are networks with two types of nodes, users and items, repeatedly interacting over time. The problem we are tackling is that of interaction prediction, that is, given a user, Alice, and time t, we seek to predict the most likely item that Alice will interact with at time t. This has applications in many domains, for instance, recommender systems. There are existing studies addressing the same problem. In this slide, we will briefly look at one family of closely related algorithms. These algorithms rely on learning dynamic embeddings for users and items at every interaction. That is, when you and I interact at time t, they generate the embedding vectors u sub t and I sub t. The embedding of u at time t is learned using first its own embedding at time t minus 1, which is this one, and second the item embedding at time t minus 1 as well, this one. The same is true for the item embedding. Then during prediction, given a user and timestamp, the item whose embedding is close to the user embedding at time t minus 1 is predicted using k-nearest neighbors algorithm. This formulation is clearly recursive, which leads to sequential training as opposed to mini-batch training, and this is not efficient. Some studies have proposed specialized algorithms for mini-batch training. However, first, the number of instances vary across batches, and second, in the worst case, a batch might have a single instance, which brings us back to the same problem of sequential training, at least partially. And there is no guarantee that the number of batches within a single instance is not significant. Therefore, in this study, our goal is to alleviate this problem of recursive dependency to improve both the efficiency and effectiveness of this family of algorithms. Before moving to the discussion of our algorithm, let us briefly define a few notations which we will encounter in the coming slides. Temporal interaction networks are represented as a sequence of events or logs sorted by time, where each event is a triplet containing a user and item and the interaction time. Second, interaction logs or events associated to a user and an item are defined as follows, which are this and this. In addition, we have the k-recent events that happened before time t, both for the user and an item, and we denote them using these two symbols. This is one of the key components that we leverage to avoid recursive dependency, as we shall see in the coming slides. Finally, we have L sub u and L sub I, which are just the indices of the last events of user u and item I. Now let us discuss the details of the proposed method, which is deep-read. Deep-read has three key ideas. The first is learning the way users and items interact with each other, and we do this from a long-term and a short-term interaction perspective. The second is, which is this one, learning the delay patterns, which helps us to identify fresh interaction patterns, which are commonly considered to have an impact on future interactions. Finally, we learn compatibility across the interaction logs or events of users and items. And this is the architecture of deep-read. Its inputs are an event and a hyperparameter k. The first component, which is encoding, allows us to learn the interaction and the delay patterns, the first two objectives in the previous slide. The second module allows us to learn the compatibility and ultimately generate user and item embeddings at time t. The first element of the encoder learns long-term interaction patterns. To this end, we use an identity-based embedding. That is, for every user u, we learn an embedding vector e sub u, and the goal is for this vector to capture the most dominant or prevailing context or interest of this user For example, this user is mainly interested in action movies. Second, the embedding uh, is learned using all the interaction events where U is involved in, which are all these interactions involving user U. And we do the same for the item, and the meaning of the embedding is equivalent to that of the user. The second element of the encoder learns short-term interaction patterns. And it has two components, which are the contextualization of interaction events and modeling of recurring interaction patterns and delay patterns. In the contextualization, the key idea is that for every user, first, we only leverage the k recent events that happened strictly before time t, that is this one. Second, we inject context for each of the user events. That is, first, for each event, that is this event, we associate semantics using the long-term embedding, which is this E sub IL. In addition, we augment delta, which is the difference between the current event, this one, and this particular event, and the current timestamp, which is T. We do the same contextualization for the item. Finally, we model recurrence and delay using time-aware recurrent neural network, which gives us these high-level features for both user U and item I at time t. The last component of DeepRed learns the compatibility across the recent events of the interacting user and item. The goal is to capture how well the contextualized events agree both in terms of semantics and delta. This is based on the assumption that the interaction events between the interaction event between user U and item I at time t is caused because of some contextual agreement. For example, we see that the most recent events for both U and I are in the same genre sci-fi, and the delta is also close to zero. Therefore, to learn this phenomenon, we use a simple attention mechanism. And this allows us to derive a k-dimensional attention weight vectors, which encode the impact of each of the recent events in causing the current event that happened at time t. Finally, we use the attention coefficients to compute the weighted sum of the high-level features and project the user item embeddings at time t as shown here. Therefore, we can see that by relying on the semantics of recent events, we have effectively removed the recursive dependency to learn these dynamic embeddings. The model is trained by maximizing the compatibility of the embeddings that we have just learned at time t. This is equivalent to minimizing the L2 distance between these embeddings, as shown in this equation, and plus a regularization to avoid the trivial solution, which collapses the embeddings into a subspace. To validate the proposal, we perform empirical evaluation using 3 real-world datasets from Reddit, Wikipedia, and Last.fm. The datasets contain 1 month of interaction, and interactions are significantly repeated for Reddit and Wikipedia, as you can see here, whereas repetition is very sparse in the case of Last.fm. The setting of the experiment is as follows. We compare our method with 3 family of methods. First, we have sequence models. These are different flavors of RNN. Second, those similar to DeepRed. These are the recursive methods which we mentioned at the beginning. Finally, we have a method for general temporal graph embedding. The datasets are partitioned by respecting the order in time, and the first 80% is used for training, the next 10% for validation, and the final 10% for testing. The task is next item prediction, that is, given a user U and a timestamp T, we want to predict the next item that U is likely to interact with. And the quality of the prediction is evaluated with respect to the ground truth event containing U and I at time t. The prediction strategy is that we use the embedding of U, which we have learned during its last interaction that happened just before the current time. Then we find the k nearest item embeddings for this embedding and return their ID. We use the mean reciprocal rank and recall at 10 to evaluate the prediction quality. The results of these experiments are reported in this table. This highlighted row reports the performance of DeepRed. Apparently, we can see that DeepRed outperforms the baselines in almost all the cases. More importantly, though, notice that there is a significant difference between the mean reciprocal rank and the recall at 10% for all the baselines. However, for DeepRed, this difference is very small, or relatively very small. This shows that DeepRed consistently ranks the ground truths higher in the ranked list than the baselines. The second best algorithm, which is Jody, is better than DeepRed for Reddit when we look at the recall at 10%. Nonetheless, DeepRed is better for the rest of the cases. In addition, when we look at the recall at 1 for Reddit, with respect to Jody, we see that Jody, the performance of Jody drops significantly from 0.85 to 0.64. Whereas we see that the difference is very small in our case. In the next experiment, we analyze the effect of the hyperparameter k, small k, which we use to determine the number of recent events. As you can see from this figure, across different datasets, k has different effects. Particularly, notice that for last FM, prediction quality increases proportional to k. Recall, in this dataset, interactions are rarely repeated. And this finding shows us that we need to look further back in the past to extract meaningful interaction patterns. The second best performing algorithm was Jody, reaching just 30% in terms of mean reciprocal rank. And this demonstrates that in addition to the efficiency bottleneck, the recursive dependency limits its power to learn long-range interaction patterns as a result of vanishing gradients. Finally, we carried out an experiment to compare the runtime performance of algorithms. The figure shows the time it took for an algorithm to finish a single epoch of training using the Reddit datasets. On the x-axis, we have time in minutes. On the y-axis, we have the algorithms. The highlighted region shows that DeepRed is the fastest among the bunch. However, we are more interested to compare DeepRed with the closely related recursive baselines highlighted in black, and we see that DeepRed is in fact much faster than these baselines. We want to highlight that we have borrowed the numbers from Jody's paper for most of the experiments, including this experiment, because the source code for most of the baselines was not available. For some of them, though, we reproduced the results by rerunning them on our machine. Since Jody is the second best performing algorithm, and it is the one which has a specialized mini-batch algorithm to improve efficiency, we rerun it on our machine to see if there is any difference in terms of computational time. Indeed, there is a difference, and it took 15 minutes to finish a single epoch of training on Reddit dataset on our machine, and this further establishes the efficiency of DeepRed. Thank you very much for your attention, and if you have questions, please find us during the online session of the conference or through email.